Uh, Thanks, Keita. Thanks a lot to the organizers for the invitation. I'll talk about some stuff that's rather unusual for me as a topic. Those of you who know me know that fragments of PA is something I know much more about than I do about Scott ranks. I knew next to nothing about Scott ranks, say, half a year ago. And well, this is also maybe not the most natural topic for this workshop. I'll come to that in a moment. But it is joint work with my colleagues from Warsaw, Mateusz Wełyk and Patryk Szlufik, who is here, who is Mateusz's PhD student. And those guys got me to work on this. I mean, they were the ones who pulled me into this project. So this is a sort of strange topic. It's not really reverse mathematics. And of course, the true reason why I'm not giving a reverse mathematics talk is that I don't have results in reverse mathematics proper that would be sufficiently interesting and sufficiently new that I would like to talk about them here. But I invented some bogus reasons, so why I'm talking. So one piece of bogus motivation is that, well, many people who do reverse mathematics are computability theorists, and at least some computability theorists care about Scott ranks. So maybe if I talk about Scott ranks, a few people in the audience at least will be somewhat interested, and maybe all should be. I dress this up as a deontological inference of debatable validity. And another sort of bogus reason, bogus in the sense that I'm not really convinced I believe in it. I pretty much don't, but still. Scott ranks are a way of classifying structures, and proper subtheories of Peano arithmetic matter in reverse mathematics in various areas. There is the study of what you need to prove computability theoretic theorems, that's reverse recursion theory. Of course, fragments of PA and their models matter in understanding first order consequences and pi-111 conservation arguments. So it's kind of nice to understand what the models of these theories are, and any sort of way of classifying them and understanding their structure is potentially useful. This is not completely bogus in the sense that once we started working on this and once I got involved in it, I found myself using techniques and ideas that earlier turned out to be fruitful in genuinely reverse mathematics contexts, like automorphisms of structures, which turn out to matter for reverse mathematics, like the low basis theorem in a place. So maybe there'll be some sort of connection in the other direction as well, from this work to reverse mathematics proper, but I wouldn't count on it like very, very soon. Okay, so what are Scott ranks? I assume that many of you know this infinitary logic L omega 1 omega, but maybe not all do, and probably some of you have just this cursory acquaintance with it that I had not that long ago. So it arises from first order logic by allowing countable conjunctions and countable disjunctions. So if you've got a countable set of formulas, let's assume that all these formulas, well, their union only uses finitely many free variables. Then you can take their conjunction, and then you can take their disjunction. You can allow formulas, technically you could take a disjunction of, say, formulas that altogether have infinitely many free variables, but the thing is, you can only quantify finitely many times along a branch in the syntactic tree. So such a formula with infinitely many free variables never becomes a subformula of a sentence. And in the end, we care about sentences. So we might as well make this assumption that we only take conjunctions of countably many formulas when together they have just finitely many free variables. That's it. That's the definition of the logic.
Logic in quotation.
Come on, I mean, what sort of logic is that? Logic should be finitary and proofs should be finitary. Everything else is, I mean, it might be useful mathematical object, but it's...
At most 4 symbols. Otherwise.
Well, I wouldn't have anything against like 10 or 12. About the horizon of my imagination. So it's a perfectly fine mathematical object. I don't think of it as a logic in the strict sense. So that's where the square quotes are from. And I think I was first talking about this to models of piano arithmetic, people who are like more model theorists than I am, and they think that L omega 1 omega is a logic, so I felt the moral obligation to put the scare quotes to.
Well, there's a model theoretic
Yeah, yeah, sure, I know it, yeah. It deserves the scare quotes in its full generality, right? Anyhow, so the important thing, or one of the important things about this logic, is that for any countable structure, you can characterize it in L omega 1 omega up to isomorphism within the class of countable structures. So if you like thinking in terms of Ehrenfeucht-Freise games, for example, as I at least used to do, there is, for each structure A, for each countable structure A, there is a sentence of L omega 1 omega, such that if any other structure B satisfies the sentence, then the duplicator, the second player, will win the infinite game on these two structures A and B. This corresponds to being equivalent in an even stronger infinitary logic, L of infinity omega. And if you have two countable structures and the second player can win the infinite Ehrenfeucht-Freise game on them, that gives you a back and forth isomorphism. So it's a very nice and interesting theory. It's not that hard to prove. And any sentence of that nature that characterizes a structure A up to isomorphism among countable structures is called a Scott sentence for A. And the Scott rank is basically the complexity of the simplest Scott sentence for a structure. So if we want to measure complexity of sentences or formulas, we need some sort of complexity hierarchy. And just like in first order logic, there is a typical quantifier alternation hierarchy. We have a similar one here where you sort of merge disjunctions with existential quantifiers and you merge conjunctions with universal quantifiers. So the zero level of this hierarchy is just a quantifier free first order formulas. Then you get a new pi level by taking conjunctions of universally quantified formulas from earlier levels, and the sigma level is defined dually, right? It's disjunctions of existentially quantified formulas from earlier levels. And there is a number of definitions of Scott rank, but the one I'll be using here was proposed by Antonio Montalban in a paper 10 years ago. I've heard it, I've seen it called the categoricity Scott rank as well. And this is a very simple definition. The Scott rank of a structure is the smallest alpha such that the structure has a pi alpha plus 1 Scott sentence. The reason for alpha plus 1 will, I think, become apparent in a while. The advantages of this definition is that it has many equivalent characterizations, so it's pretty robust. There are other definitions possible that all are equivalent up to a small finite constant. So we won't care too much about them, but this is the one I'm working with, to get precise results. So this is and it's some sort of measure of the complexity of a structure, how hard it is to characterize it up to isomorphism as a countable structure. So people do care and have studied Scott ranks of particular structures, of models of specific theories like groups or rings or whatever, or orders. There has also been studied, there were important results of Harrison Trainer, for example, a number of years ago, on what the set of Scott ranks of a theory can be. And if you've got a theory, we can define that as a concept. We can say what Scott ranks models of that theory might have. We call that the Scott spectrum. So the Scott spectrum is just the set of ranks that models of that theory might have. So, for example, for an omega categorical theory like dense linear orders without endpoints, DLO, the Scott spectrum will be a singleton, obviously. For DLO, it's one. You can work out the axiomatizing sentence yourself, I'm sure. In contrast, for example, linear orders can have all possible Scott ranks. Scott rank is always countable, of course. I mean, finally you're countable, but there is some oddity about Scott rank 0, so please just ignore it, depending on whether you allow finite structures, the empty structure, whatever. different. It might be the singleton linear order that has Scott rank 0, or the empty one, or none at all. So just ignore that. But Scott rank 0 won't bother us much in what I have to say. So basically, up to that triviality, linear orders can have any Scott rank at all. And what is perhaps closer to my topic today, people have started not that long ago caring about Scott ranks of models of arithmetic, which to me sounds like a pretty natural topic once you have this concept of Scott rank. The first paper in this area, it was published just 2 years ago, I guess, by Montalbán and by Dino, who's here, was about Scott ranks of models of Peano arithmetic. It doesn't take long to figure out. This might be very slightly language dependent, but for almost any reasonable choice of language of Peano arithmetic, the Scott rank of the standard model is going to be 1. Basically say that every element is 0 or 1 or 2 or 3 or whatever, and the natural relations hold between these things. On the other hand, it's not that hard to prove. One of their results was that all non-standard models of PA must have infinite Scott ranks. And this was like the main result of their paper. In fact, every infinite ordinal alpha is the Scott rank of a model of Peano arithmetic. So the Scott spectrum of PA is singleton 1 plus infinite ordinals. They also showed that well, each completion of PA, since PA has definable Skolem functions, each completion of PA has a pointwise definable model, which is actually a prime model of the completion in the model theoretic sense. And those pointwise definable models, except for true arithmetic, that's the standard model. So pointwise definable models of false completions of PA have Scott rank exactly omega. This is pretty easy to figure out. They posed a question on whether any other models of PA might have Scott rank exactly omega, or must they have greater Scott rank? And the answer is negative, and the way I first learned about it was by refereeing Patrick's master's thesis. And now that result will form part of a larger body of work on a refinement of the notion of Scott rank for models of arithmetic by David Gonzalez, Mateusz, Dino, and Patrick. I think it's just out on the archive, like last week or something of that kind. So it's a very fresh paper. But yeah, every model of Peano arithmetic that's not a pointwise definable model must have rank at least omega plus 1. And this sort of stuff, if you care, as I do, and as my other Warsaw colleagues do, about fragments of arithmetic as well, makes you naturally ask the question, what happens for models of, say, sigma and induction? How do like lowest possible Scott ranks go up once you increase the amount of induction without going all the way up to full PA? So that's the topic of this talk, and we'll see how much of the more technical material I cover, but that's what I want to talk about. I might have not emphasized on the first slide, this is definitely work in progress. So I kind of think that we've proven enough stuff to write it down, and I'm sufficiently confident about the stuff that I'll state as theorems that it should be true. And once we find the time, this will be written down properly. Right now, the paper is a big mess. But maybe there are still possibly some bugs in the proofs, and not all the results are like in the neatest form that you would like. There are open problems that you would like to solve, but maybe we won't for now. We'll see. So what about Scott ranks of models of fragments of PA? Let's recall what fragments of PA are, the usual ones. This talk will be about the usual ones. So, PA is axiomatized by the induction scheme. So if you restrict the induction scheme to sigma n formulas, you get the theory I sigma n, and the I sigma n's form a strict hierarchy whose union is full PA. And between sigma n and sigma n plus 1 induction, there is this intermediate theory, sigma n plus 1 collection. In arithmetic, collection is the same thing as bounding. So sigma n collection is, you need to have delta zero induction, otherwise it doesn't work. Full collection without any induction at all is a very, very, very weird theory. But you say, collection says that if for all x is below a bound, there is a y, then there is a bound on the y's. Okay? So this is a natural property. And sigma n collection is delta n induction by a result of Ted Slayman from 2004 or something around that time. Note, a note for both those of you who are experts in this stuff and those of you who might not be experts and might not want to care. Generally, I will be sort of assuming they have the exponential function. Well, they have an axiom saying that the exponential function is total. So the models that I will be considering all have this property that for every x there is a 2 to the x, which allows us to have a convenient identification of finite strings with first order objects. Actually, so when I'll be talking about I delta 0 or B sigma 1, which are the two theories in this hierarchy that don't prove the totality of exponentiation, what I really have in mind is I delta 0 plus x and B sigma 1 plus x. But most of these results actually don't need x, but that's not the direction I want to go in. It's technical, bounded arithmetic-y stuff that I want to ignore for the purpose of this talk. So generally x is there. And if I really want to emphasize that it's there, I'll put it in explicitly, but in general, it's there. Okay? Yeah, you could add, for example, the graph of exponentiation into the language if you want to. The graph of y equals 2 to the x. That's actually delta zero relation, so it doesn't change much. And let's say that you stick the axiom for every x there is y equals. No. That I do want to have the option of having just models that you are just closed under elementary recursive functions, for example, and not under such monsters as the tower function, not to mention even larger primitive recursive. That's too fast growing for me. Peano arithmetic is the union of this intertwined hierarchy of I sigma n levels and V sigma n plus 1 levels. And accordingly, models of fragments of arithmetic split into two categories. A model of I delta 0 that's not a model of PA can be one of two things. It can either be a model of sigma n induction and not the next level of collection. That's what we call an I model. And the most classical example of I models, these classical examples come from a paper of Kirby and Paris from 1978. So they're almost as ancient as the Joker's paper that was mentioned yesterday. So it's almost as venerable and older than the Gliot paper, right? So the classical example of a model of sigma n induction that doesn't satisfy sigma n plus 1 collection is you take a model of a strong enough theory. Sigma n plus 1 induction is actually a bit more than enough, but let's take sigma n plus 1 induction. And then you take those elements of this model that are, their singletons are sigma n plus 1 definable without parameters. So for example, if this model satisfies inconsistency of PA, then the smallest proof of inconsistency will be a delta zero definable element, so it will definitely be there. And these sigma n plus 1 definable elements, they form a submodel of the original structure we started with, the original structure, I call it A in this picture. There's a certain amount of elementarity, there is sigma n plus 1 elementarity between the two structures, and this structure of sigma n plus 1 definable elements, it's never an initial segment, unless it's just the standard elements. It's never an initial segment of the original structure. This is indicated by these black gaps. So the black part does not belong to the model we're building. And it's, as long as it's non-standard, it's a model of sigma and induction, but nothing more. That's it. It's not a model of the next level of collection. The other kind of model of a fragment of arithmetic is called a B model. So that's when you have collection, but not the next amount of induction. So sigma n, but not collection, but not induction for n greater or equal to 1. For 0, but that doesn't really make sense. So if we start counting at 0, it's going to be sigma n plus 1 collection. And a classical example is you take a model obtained as above, which, as mentioned, is never an initial segment of the ground model you started with, of the structure A here, and you close it downwards. So that initial segment, generated by the sigma n plus 1 divinables, assuming the original structure A was strong enough, is going to be a model of sigma n plus 1 collection. So it satisfies just a little bit more of arithmetic than the sigma n plus 1 definables themselves. So these are the classical examples. They're not really canonical in any strong sense. It's not the case that any I model is elementarily equivalent to a model like this, for example, and the same is also true for B models. So they're just the ones that came up in the first proof that these theories are distinct, basically, and they're sort of nice and natural to have and very ancient and venerable, but they're not really canonical in any proper sense. These two kinds of models, they behave very differently model theoretically in general. So it really is a distinction worth making, but I won't. Well, you'll see an example of this, but not. I won't get into that too much. Okay. So yeah, a basic question that we started with, and this is one that I would like to cover. Yes, Peter. In general, no. So for example, actually these two classical examples are like basically never resplendent, right? Because for countable structures, resplendence is the same thing as recursive saturation. And these structures are extremely non-saturated. So for example, look at the I model at the top. Definable elements. You can form a type saying, well, I'm an element, well, I'm X, and I'm not defined by this definition, not defined by that. That's a type, but it's clearly not realized here. So these particular guys are extremely non-resplendent. And in fact, the resplendent models will all have Scott ranks. I can tell you what this resplendent countable models, what the ranks will be. Omega plus 1 always, exactly. For pretty general reasons. So it's not completely trivial, but it's not a hard fact to prove. This was known for models of PA earlier. Excuse me? I mean countable. We're doing countable models. We're counting Scott ranks for countable models. That's where the concept makes most sense, right? That's where it's kind of natural. I don't know what the Scott rank of uncountable models is. I'm sure some people do, but if it makes sense, and then if it does, then what the definition should be. But I don't. Okay, so our basic questions were at the start of this research. Well, firstly, what sort of lower bound does a certain amount of induction put on the Scott rank of a theory of a model? We always have the standard model, right, which has Scott rank 1, but TA insists that otherwise the Scott rank has to be at least infinite, so how does that grow with n? Does it grow with n in any natural way? And secondly, what the Scott ranks are of these most classical examples. So that set of questions is, I would say, solved to our satisfaction now. So first, I will prove or tell you how three things are proved. Namely, first of all, a model of B sigma n, of sigma n collection, must have, a non-standard model, must have rank at least n plus 1. And this is tight, as witnessed by both kinds of classical examples. So, a B model of exactly sigma n collection, formed by taking the sigma n definables and closing downwards, has rank exactly n plus 1. And an I model of sigma n plus 1 induction, which also happens to be a model of sigma n collection, doesn't satisfy an I model of sigma n induction, which is also an example of a model that satisfies B sigma n, but not B sigma n plus 1, a pointwise definable model of this sort will also have Scott rank exactly n+1. So the classical examples witness the minimal possible Scott rank. So the jump in minimal possible Scott rank occurs at collection levels of the hierarchy, not at induction levels, and it's witnessed by all the most classical examples. So a non-standard model of I delta 0 may have Scott rank 1. That's, for example, the sigma 1 definables in a well-chosen structure, or more. A model of B sigma 1, and the same thing holds for I sigma 1, may have rank 2 or more. This is actually a list of the Scott spectra of these theories. So, for example, the Scott spectrum of B sigma 2 is from 3 up to omega 1. And same for I sigma 3. So that's, if you want to know the Scott spectra of the B sigma ends and I sigma ends, they're here. Later, I will want to say something about what we know about Scott ranks of theory, Scott spectra of theories obtained by taking a specific level in the induction hierarchy and forbidding any more induction. So that's a false theory. And yeah, you get more information by asking what the Scott spectra of models of that sort of theory can be. Okay. Yes? Yeah, so, well, this is just this, I guess, because I'm not negating more induction here, just this is actually trivial from the statement and the earlier Montalban-Roseger results, right? I think so. I mean, it's true anyway, but I think it just follows trivially because, well, you'll have a model of B sigma 1 of rank 2, then a model of B sigma 2 with rank 3, and so on by the tightness of these bounds, and then all infinite levels are realized by PA. Yeah, that's an interesting story about which we know some non-trivial things, but not everything. I plan to at least state what we know and maybe tell you something about how we prove it. The J's were the cuts. Yeah, and I think I've got the indexing right. I mean, it's very easy to get confused about n and n+1, but I think in the slides I actually made a conscious effort to get this right. So if you were, those are the B models. Yes. So I'll try to sketch some proofs of bounds on Scott ranks, and the main tool for this is one of the reasons why Montalban defined his Scott ranks in this particular way and not another one. So what he proved a whole list of equivalent conditions to having Scott rank alpha in his notion of rank. And the one that will be technically useful for us is in terms of definability of automorphism orbits. So a countable structure has Scott rank alpha. Again, ignore alpha equals 0. If every automorphism orbit of a finite tuple in this structure is sigma alpha definable in this infinitary logic sense without parameters. So that's an equivalent characterization of Scott rank. So you can prove bounds on Scott ranks of structures by estimating the complexity of how difficult it is to define automorphism orbits. And for many kinds of models of arithmetic, we do know things about the automorphisms, which helps a lot. There are other characterizations of the Scott rank in terms of, how hard it is to recognize whether something is a copy of the structure in the Borel sense, or how hard it is to compute an isomorphism between two copies. But this is the one in terms of definability of orbits is the one that we will actually be using. So let's say a bit about how the lower bound is proved. How you prove that a model of sigma and collection must have rank at least n+1. By model, I mean non-standard model, right? We eliminate the pathological case. So we'll use a simplifying assumption. There is a very weird case that I'm not sure really appears, and anyway, there's a cheap trick to eliminate it, but I don't want to get into that, but it appears somehow relevant to this. we'll assume the following, that the automorphism group of this model isn't too large. Namely, we'll assume that there are two non-standard elements, say A and B, such that no automorphism maps A above B. So this is a very tame condition. I mean, any sane model satisfies this. If you have a single definable element, like an inconsistency proof or whatever, like a single delta zero, yeah, if you have a definable element, that's already enough. You just can't move it anywhere, so you can't move it arbitrarily high. But this was, and you can, this is without loss of generality, in fact, but I don't know, models that violate this, non-standard models that violate this definitely do exist, but the only examples I could come up with satisfy true arithmetic. And it's sort of, if a model that violates this satisfies a certain amount of induction, then it satisfies a certain piece of true arithmetic, but it couldn't prove that it has to satisfy all of true arithmetic. So it's sort of a very weird thing to violate. So just assume that we have this, and we can do it without loss of generality, and this will be needed. So here are three things to know about models of collection, models of induction that we will use. One, if you've got a non-standard model of sigma m induction, where m is just a number, then the pi m, in the usual arithmetic sense of pi m, type of an element is coded in the following sense. There is a number, say e, such that for any pi m formula, any standard pi m formula, this formula is true about our number a if it belongs to this number e, this code considered as a set. Okay? So this is, for those of you who do reverse mathematics, this is basically sigma m induction being sigma m bounded comprehension. There is nothing deeper here. So this is just, plain stuff. Then there is this thing that is published in this paper by Dino and elsewhere and others, but I learned from it I learned about it from Patrick's thesis written under Mateusz's supervision. So I called the Wełek-Szlufik lemma just to annoy non-Poles. It's a cool sounding name, I think. And this is a I think non-trivial technical. It builds on something that Montalban and Ossegar proved, but I think it's a nice generalization. If you've got a model of sigma m induction, so the m is the same here, and you've got two tuples that share the same pi m type in the arithmetic sense, then they share the same infinitary pi m type. So the index m is a finite number, but the types on the right are infinitary. So they can allow infinite disjunctions and conjunctions. So this is an interesting thing. Sigma m induction is enough to give you this for pi m. And finally, this is like a classical fact. It's probably Paris and somebody in the 70s. I'm not exactly sure who proved this. Maybe Keita knows, but I don't know. Sigma m collection is equivalent to the sigma m pigeonhole principle. So just the statement that there is no sigma m definable injection or even injective multifunction from x plus 1 elements to x elements. That's what a collection is. Okay, so let's have this model of sigma n collection with this property that there is a non-standard element A that you cannot move above a certain other non-standard element B by an automorphism. And let's prove that this model has Scott rank at least n plus 1. So assume otherwise. Assume that it has Scott rank n or less. So the orbit of every element, let's take an arbitrary element, call it C, has an infinitary sigma n definition. Now, the sigma n definition has some disjunct that's actually true about C. That disjunct begins with some existential quantifier block. Doesn't matter. We're in arithmetic. We can assume it's just one quantifier. There's a witness for that. So D is a witness that C is in a specific automorphism. Now, the usual pi n minus 1 type. So once you take these initial existential quantifier off, you'll be left with an infinitary pi n minus 1 formula. There is a small non-standard, there's a small non-standard element coding the usual arithmetical pi n minus 1 type of the pair CD. And, well, I'm cheating here slightly. This is not induction for exactly this formula, but if you take the code of not just the standard formulas, but some small non-standard piece of the pi n minus 1 type of CD, then there is a smallest pair with the same pi n minus 1 type. This is just, we have enough induction. So there's like a smallest pair with the same type as C and its witness D. Let's call this pair C0, D0. And by this lemma that, agreeing on finitary pi types gives you agreement on infinitary types, these two pairs, CD0, D0, and CD, have the same infinitary pi n minus 1 type. So C and C0 are in the same automorphism orbit. So say that C is H of C0 for some automorphism. But C0 is smallest such that something, or it's a projection onto the first element of a smallest pair or whatever. So it's sigma indefinable with this very small non-standard parameter E here. In particular, it's sigma indefinable with a parameter below A, because this code can be as small as you want. So C0, our arbitrary element C here, is sigma indefinable with parameter H of E. Okay, so if C0 is definable with parameter E, then C being H of C0 is definable with parameter H of E. And H of E is below B by our assumption about the automorphism group. So this guy, C was arbitrary, so everything is sigma n definable by a standard sigma n formula with a smallish parameter below this number B here. But that's a very brute violation of the pigeonhole principle. So that's a violation of collection, and we're done. That's how we can prove the lower bound, and it really is about collection and not induction by the complementing upper bounds. So let's talk about the upper bounds briefly. The case of these pointwise definable I models is essentially trivial. So why is a pointwise sigma n plus 1 definable model? Why does it have Scott rank exactly n plus 1? It must have rank at least n plus 1 by the lower bound. Now, what are the orbits in a pointwise definable models? They're singletons. And these singletons have sigma n plus 1 definitions. It's not totally obvious, it's borderline, but it's not totally obvious that the sigma n plus 1 formula is also an infinitary sigma n plus 1 formula because of the zero level. The zero level in the arithmetical hierarchy is bounded formulas. The zero level in the infinitary hierarchy is quantifier-free formulas. But we're assuming the exponential function, and we've got MRDP, so we're good. This is actually a somewhat important thing, and it works in arithmetic, but not in some other contexts. But yeah, so every orbit happens to be a singleton, and it's n plus 1 defined. So that's how you prove how you find the exact Scott rank of a pointwise definable I model. So what about the J models? Well, here the story is a bit more complicated, or at least these, cuts generated by definables, J models. Again, let's take the initial segment generated by the sigma n definables. That should have Scott rank n plus 1, and again, I'm pretty sure I got the indices right. It was one of the harder things in preparing this talk. So yeah, again, the Scott rank has to be at least n plus 1 by the lower bound. The upper bound is different now. In contrast to at least some I models, all B models have lots of automorphisms. This is actually a relevant to reverse mathematics fact. So if you were at Keita's talk yesterday about proof speedup and how proof speedup can already imply non-conservativity, and how pi 1 conservativity can be equivalent to pi 5 conservativity for some particular principles. Underlying a large part of that is actually the fact that B models have lots of automorphisms. It's hidden deep inside the syntactic stuff that, or computability theoretic stuff that Keita stated, but it's there. So B models have lots of automorphisms, and let's look at this model, this cut generated by the sigma undefinables. It's a countable model, so let's list the sigma undefinables externally. It's just a matter of convenience. Let's give them numbers. They will not be numbered in increasing order in general. I mean, it's their order type might be unpredictable. It doesn't have to be omega. So let's just have these sigma undefinables here, and you can prove. This is not really surprising to people who have studied this sort of thing, but it's non-trivial. I actually have to work with some overspill, and I need this model A above it. So you can actually prove that two tuples are in the same automorphism orbit. Two tuples R and S are in the same automorphism orbit if for every delta zero formula, and each and every one of these sigma undefinable elements, the tuple R satisfies that formula with that definable element as parameter, exactly if the tuple S satisfies the same formula with that same parameter. So being in the automorphism orbit, and this is, it's not very hard, but it's not completely trivial here, is the exact same thing as satisfying the same delta zero formulas with the sigma undefinable things as parameters. And well, so, being in the orbit of R is defined by saying, take a conjunction over delta zero formulas and over definable elements. You satisfy those that our tuple R satisfies. That's a countable conjunction of delta n, arithmetical delta n statements. So it's pi infinitary n, and that's infinitary sigma n plus 1. And we're done. Okay, the motor of this proof is here. And it's like, I don't know, 1.5 pages or something of that argument. So these are the basic results. We have the Scott spectra for each B sigma, and we have the Scott spectra for each I sigma n. Now, what do we know about the Scott spectra for I and not B, and for B and not I, which is it's quite interesting, I think. So the case that this is a sort of more tentative part of our work. I think the results are correct, and the gaps in our knowledge are definitely still there. So if you want to know what the Scott spectrum of I sigma n and not B sigma n plus 1 is, we know that it contains n plus 1 because we just proved that. It actually contains everything above n plus 1, possibly except for n plus 2. Which we don't know about. That's an open problem at this stage of our work. And as usual, B models are more challenging in some sense. We know that the Scott spectra of B and not I contains n plus 1. It's easy to prove that it also contains all infinite ranks. And it also contains cofinally many finite ranks. Basically, for any finite rank that you give me above the n plus 1, I can give you a model that we can estimate the rank up to a plus or minus 1. So it looks like we have in any interval of length 2, we have a model of that rank, and I expect that it's going to be all but finitely many above n plus 1, or even all about n plus 1, but we can't get the precise calculation to work there. I did want to say, and I still have time to say it a bit, at least about the I model case. So how do you get these models of sigma and induction, but nothing more, of ranks above n plus 1? So this argument splits into two cases. The mostly boring infinite case and the less boring, I would even say somewhat interesting, higher finite case, which builds on similar ideas but is more challenging technically. So how do you get infinite Scott ranks of I models of I sigma n? Well, again, you do the sigma n plus 1 definable elements construction, but the model in which you're defining these things and which tells you what the definitions are and which tells you what the formula is no longer a model of, it's no longer the standard model. So definition no longer means standard definition. Your model is now some kind of non-standard model of Peano arithmetic with the correct rank. So you take that model You produce an end extension of it by the arithmetized completeness theorem, low basis theorem, or just arithmetical basis theorem. In fact, that's enough. Whatever you want to do. So you produce an end extension of your model, now pretending to be the natural numbers, your model M of PA. You produce this end extension that satisfies enough induction and is interpretable in M, and then you take those elements of this end extension, I call it H for Henkin model of a certain completion of something. You take those elements of this model H that M believes to be sigma plus 1 definable. Some of these definitions will be non-standard. For example, every element of M will be definable by X equals a non-standard, potentially non-standard numeral, right? So that's a larger thing. And if you do this correctly, then this structure M you started with and this pseudo pointwise definable structure K are going to be bi-interpretable in the usual first-order logic sense. So they're going to be interpretations without parameters in both directions, and each of these models will recognize that its copy inside the other model is isomorphic to the model you started with. And that if you've got such bi-interpretability, then for structures of infinite rank, that actually implies that they have the same rank. Because the rank changes just by an additive constant on the left, right? If you add a finite number to an infinite ordinal on the left, then it's the same number. So it corresponds to inserting some definitions of how the relations are defined in the interpretation very deep down in the syntactic tree of the formula. So that does not increase in infinite rank. So this is a sort of boring case. The higher finite case for I models, that's more fun. So we again do the same thing. We produce what a certain model believes to be the pointwise definable elements, well, the sigma plus 1 definable elements of a certain Henkin structure. Except that now this model that's doing the defining is no longer the standard model of arithmetic, is no longer the model of PA. It might be a model of very weak induction. So it might be the case that you want to produce a model of I sigma 7, and you're working in a model of I sigma 1. So you have to have a well-chosen model. We want to produce rank n plus k plus 2, and we have to have k at least 1. So as you can notice, this gives us all finite numbers starting at k equals 1, so starting at n plus 3 and onwards. So let's just work with k equals 1. So let's do n plus 3. Let's have a model of I sigma 1. Let's apply the very low basis theorem. Let's have a sufficiently low Henkin model of some relatively strong theory that this model, we can assume that it had a lot of consistency statements, that this model believed to be consistent. Let's take the sigma plus 1 divinables of this Henkin model in the sense, this model M tells us what the definitions are. And we get this structure K, that M believes to be the sigma n plus 1 definables of the Henkin structure H. So we want to claim that this structure has Scott rank n plus k plus 2. For k equals 1, that's exactly n plus 3. And proving the upper bound is sort of mostly straightforward. So notice that we're talking about a model that consists of things that are sigma n plus 1 definable in the sense of a model that is itself sigma k plus 1 definable. And you somehow just write out these definitions, basically. The bound n plus 1 plus k plus 1 comes from having things that are n plus 1 definable, but in terms of a model that itself consists of k plus 1 definable elements. So the lower bound is where the work is. So let's say a few words about the lower bound. We've got this model M, it satisfies, it has to be a well-chosen pointwise definable model by sigma k. It believes that H is a Henkin structure. That's sufficiently low, so we know a lot about the elementary diagram of the structure H, basically everything. And K consists of the n+1 definables of H. How do we prove that K has rank at least n+3 or n+k+2 in general? As mentioned, the elementary diagram of this H is low delta 2. In fact, it's a bit more than that in the I sigma 1, if M satisfies just I sigma 1, so that you get everything working. It's this very low delta 2. Hence, by the lowness of H, and by the amount of partial elementarity that we have between K and H, sigma n plus K plus 2 statements about the structure, at least certain kinds of sigma plus K plus 2 statements, are sigma K plus 1 in the structure M. In particular, if you had a sigma n plus K plus 2 definition of the standard cut in K, you could use the lowness and the partial elementarity to produce a sigma K plus 1 definition of the standard cut in M. And you can choose M to consist of the sigma K plus 1 definables, or to consist of sigma K plus 1 definables, but in such a way that the standard cut is not sigma K plus 1 definable. So if you choose your M correctly, that means that this structure will not be able to define the standard cut in a sigma n plus K plus 2 way. In recursive saturation terms, this is called being sigma n plus K plus 2 recursively saturated. And on the side, we prove a lemma. This is a reduction to Tarski's undefinability of truth theorem, that sigma n recursively saturated structures, even the general theory they satisfy is kind of weakish, as long as they satisfy I delta 0 plus x. They have Scott rank at least M. So this is worse than the lower bound you get in general from induction, but overspill for the naturals gives you a certain lower bound on Scott ranks. Therefore, this model, since it doesn't define the standard cut in a sigma n plus K plus 2 way, must have Scott rank at least this number. That's how we prove the lower bound. This lemma, the lower bound on Scott ranks of sigma of partially recursively saturated models, it's a sort of interesting thing. I mean, one corollary that you get out of it is that a model of a fragment of arithmetic even, that has Scott rank, that's finite, cannot be sigma m recursively saturated for every m, so it must have a definition of the natural numbers. So all models that don't define the standard cut have infinite Scott rank. So that provides some information, for example, on what the Scott spectra of some completions of In plus B and not B can be. So for example, there's exactly one model of a given Scott rank, finite Scott rank 5, and all the other models have infinite. I will skip the B model case, maybe save for 2 quick comments. So the infinite case is done kind of like you would expect. We again mimic the cut generated by sigma m definables construction, starting with a model of PA. The novelty here is that these models are not really bi-interpretable. For some general reasons, you don't get a true bi-interpretation. One of the isomorphisms is not going to be internally definable. You can only approximate it from inside. And we have to check that this is enough to get the Scott ranks to match, but apparently it does. And the finite part, again, you try to mimic this construction, starting with a model of a weak theory, and we can't get the bounds we have on that to match exactly. It seems like we're within one, but we can't get the exact rank. So this is what we know, hopefully. Here are some questions. So the obvious questions left by these results that I described are as follows: is n plus 2 a Scott rank of a model of I sigma n plus not B sigma n plus 1? And you can see what breaks down if you try to do that proof. I mean, I delta 0 doesn't really support a low basis theorem and doesn't define Henkin models or elementary diagrams of Henkin models. Well, that's a basic thing. And what exactly is the finite part of the Scott spectrum of the theory of B models? And one question that I sort of like, that it might be easy, in fact. I don't know. We haven't thought about this deeply, but I think it's cute. We know that this is not true for piano arithmetic, but is there a completion of elementary arithmetic of I delta 0 plus x such that all of its models must have Scott rank at least omega plus 1? As mentioned, you always get rank omega plus 1 because resplendent models have that, or countable recursively saturated models have that. You can have completions of these false theories, I and not B, that enforce rank at least omega. That's clear from the proofs underlying the results I mentioned. You can have completions, that's also clear from the stuff that I described. You can have completions that will give you just one single unique model of a specific finite rank, and then all other models will have rank of at least omega n plus 1. But it's not ruled out that there might be completions that enforce rank omega plus 1. If I were to be looking for them, I'm not sure they exist, but if I were to be looking for them, I would look among completions that tell you that there is no smallest definable cut. These guys are, so in particular, they will not have you can hope that they will not have a definable cut satisfying PA. Those models are sort of mysterious in various ways. They're very orthogonal to these classical examples, all of which define the standard cut, actually. So maybe among those exotic structures, you can find something. And I think it's a cool question, frankly. Maybe one of you can solve it. And that's all I have to say. Thanks.